Good morning. Myself, Dr. Keshav Murthy TG, Associate Professor, Department of Electronics and Communication. In this video, today, I am going to derive an expression for electric field intensity at a point P due to infinite line charge. Before starting the derivation, let me explain some basic concepts so that you can easily understand the derivation. The direction of electric field due to positive charge is always assumed to be away from the charge. Similarly, the direction of electric field due to negative charge is towards the charge. If the charges are distributed uniformly over the line, let us assume positive charges are distributed over this line, then it is a line charge. The line charge density is denoted by lambda, and line charge density is defined as the amount of charge per unit length. Mathematically, the line charge density is the ratio of total number of charges to the total length of the line. That is, lambda is equal to Q divided by L, where L is the length of the line and Q is the total charges distributed over the line. Suppose if the charges are distributed over a small differential length, so in this line charge, we are assuming the charges are distributed over this small differential length. Let us say the length dl, then the line charge density lambda is equal to dq divided by dl, where dq is the differential amount of charges over this small differential length dl. And one more thing, the electric field intensity due to single point charge is given by Q divided by 4 pi epsilon naught r square into unit vector. It is possible to derive an expression for electric field intensity at some point P due to infinite line charge by using two different laws, Coulomb's law and Gauss law. Today, in this video, I am going to consider a Coulomb's law. By applying Coulomb's law, I am going to derive an expression of electric field intensity at a point P due to infinite line charge. So, let us consider a rectangular coordinate system which consists of x-axis, y-axis and z-axis. To find the electric field E at a point P due to infinite line charge, let us assume an infinite line charge which is placed along z-axis, where the charges are uniformly distributed. So the infinite line charge is placed along z-axis, and the point P, let us assume it is located on y-axis. So if you place the point P on y-axis, then the coefficient of x-axis is 0 and the coefficient of z-axis is 0. Let us assume the distance between the point P and the infinite line charge is r. Here it is difficult to find the electric field at this point due to infinite line charge, because without knowing the length of the line, it is quite difficult. So what I am going to do now, let me consider a small differential segment, both the side, positive z as well as negative z, and the distance from the origin to the small differential segment is, let us say, z. So the coordinates across z axis is z, and the x coefficient is 0 and the y coefficient is 0. Here the distance between the point P and the infinite line charge is r. So the y coordinate is the distance r, and then the distance between the differential segment to the point P, let us assume capital R. So as we know, the direction of electric field due to positive charge is away from the charge, and our point of interest is to find the electric field at this point. So the direction of electric field at this point is like this, and the direction of electric field due to this small differential segment at this point is this. So here the distance from the origin to the small differential length dz, so it is placed along z axis. So dz, which carries dq amount of charges, and the distance between the small differential length dz to the point of interest is capital R, and the distance from the origin to the point P is small r. As we know, the electric field intensity, as I told, the electric field intensity E vector at a point P due to a single point charge is given by E vector is equal to Q divided by 4 pi epsilon naught r square, where r is the distance between the point P and the single point charge, and into unit vector. So here we are getting a small differential electric field dE due to this small differential segment dz. So differential electric field dE vector is equal to dq, because the small differential segment dz carries dq amount of charges, divided by 4 pi epsilon naught into capital R square, because here capital R is the distance between the point P and the small differential segment dz, into a y cap. Here the point P is located on y axis, so it is ay vector. Suppose if the point P, you start on the 4 pi epsilon naught into capital R square, because here capital R is the distance between the point P and the small differential segment dz, into a y cap, because the point P is located on y axis. If the point P is located on z axis, then it is ax cap. If the point P is located on x axis, then it is ax cap. Here in this case the point P is on y axis, and dq, since we are assuming a line charge, as we know lambda is equal to q by L. If we consider a small differential segment, lambda is equal to dq by dl, where dl is the small differential length. So dq is equal to lambda into dl. Substituting dq, d vector is equal to lambda into dl. Here it is dz. Here we have considered dz. So divided by 4 pi epsilon naught r square into Unit vector is the ratio of a distance vector divided by the magnitude of that vector. So here the magnitude of that vector is r square plus z square. So unit vector ay cap is equal to, at this point the vector is r a y cap, and the vector at this point is z a z cap. If I take the difference between these 2 points, I will get the distance vector r. Therefore r a y cap minus z a z cap divided by the magnitude of r is square root of r square plus z square. R is the distance from this point to point P, and R is the distance from origin to point differential segment dz. So substituting this in this above equation, it is r ay cap minus z az cap divided by square root of r square plus z square. Again, differential electric field dE vector is equal to lambda into dz divided by 4 pi epsilon naught. Again, r is the distance, so square root of r square plus z square whole square into r ay cap minus z az cap divided by square root of r square plus z square. So here the differential electric field at this point due to this small differential segment is dE, and again the differential electric field at this point due to this small differential segment is again dE. So these two differential electric field dE, let us say this is dE1 and dE2, can be decomposed into vertical as well as horizontal components. Here we have considered the small differential segment dz positive side as well as negative side, and the distance from origin to small differential segments remains same. So from this diagram it is very clear that the vertical components gets cancelled because of equal in magnitude, opposite in direction. Only we will get the horizontal components. So this vertical components is with respect to z, so this z tends to 0. Next, here it is square root of r square plus z square whole square. Again, square root of r square plus z square. So dE vector is equal to lambda dz divided by 4 pi epsilon naught square root of r square plus z square whole cube into r ay cap. So here our point of interest is to find the electric field due to infinite line charge. But here in this diagram we have considered a small differential segment. So by doing integration from minus infinity to plus infinity, it is possible to calculate the total electric field due to infinite line charge. So E vector is equal to integration of minus infinity to plus infinity. Here I am going to integrate to find the total electric field from minus infinity to plus infinity. Lambda dz divided by 4 pi epsilon naught r square plus z square whole to the power of 3 by 2 into r ay cap. So E vector is equal to, I will take this lambda as well as R as a distance, so I will take outside, divided by 4 pi epsilon naught integration from minus infinity to plus infinity dz divided by r square plus z square whole to the power of 3 by 2 into ay cap. So from this diagram, so let us assume this is theta, angle between the origin to the small differential segment dz. So from this diagram, tan theta, we know that tan theta is equal to opposite side divided by adjacent side. So the opposite side is z and the adjacent side is r. Therefore, z is equal to tan theta into r. So here in this equation I need dz. So z is equal to r tan theta. If I differentiate this, I will get dz. dz is equal to r. Differentiation of tan theta is secant square theta into d theta. So that here I have got dz. So again from this z is equal to r tan theta. So by substituting that, lambda r divided by 4 pi epsilon naught integration from minus infinity to plus infinity dz is r secant square theta d theta divided by r square plus z square. Z is r tan theta, so r square tan square theta whole to the power of 3 by 2. So from this, let us assume this as equation number 1. So from equation number 1, theta is equal to tan inverse of z divided by r. So from this diagram, we are going to find out an infinite line charge. I mean, we have considered the infinite line charge. So if z is infinite, then theta is equal to tan inverse of infinite divided by r. So theta is equal to tan inverse of infinite. So it is pi by 2 if z is equal to minus infinite, because we are going to find out an electric field due to infinite line charge. So if z is equal to minus infinite, theta is equal to tan inverse of minus infinite. So theta is equal to minus pi by 2. So if z is equal to infinite, then theta is equal to pi by 2. If z is equal to minus infinite, theta is equal to minus pi by 2. So in order to find out a total electric field, so this equation you can write it as lambda r divided by 4 pi epsilon naught integration from minus pi by 2 to pi by 2. You take this r outside, so it is r square secant square theta divided by r square plus r square tan square theta whole to the power of 3 by 2. Again, we will take this r common. So E vector is equal to lambda r square divided by 4 pi epsilon naught integration from minus pi by 2 to pi by 2 secant square theta d theta. So if we take r square whole to the power of 3 by 2 common, so in this equation, so if we take r square whole to the power of 3 by 2 common, then it is 1 plus tan square theta. So it is 1 plus tan square theta whole to the power of 3 by 2 into ay cap. So E vector is equal to lambda r square divided by 4 pi epsilon naught. Here 2 gets cancelled. So r cube integration from minus pi by 2 to pi by 2 secant square theta divided by 1 plus tan square theta is nothing but secant square theta whole to the power of 3 by 2 into ay cap. So E vector is equal to lambda divided by 4 pi epsilon naught r integration from minus pi by 2 to pi by 2 secant square theta divided by secant cube theta. 2 gets cancelled, so secant cube theta into ay cap. So again, by doing simplification, E vector is equal to lambda divided by 4 pi epsilon naught r integration from minus pi by 2 to pi by 2 1 divided by secant theta into ay cap. So 1 over secant theta is nothing but cos theta. So E vector is equal to lambda divided by 4 pi epsilon naught r integration from minus pi by 2 to pi by 2 cos theta into ay cap. So here in the numerator there is a d theta, so we will carry this d theta. Therefore, E vector is equal to lambda divided by 4 pi epsilon naught r integration of cos theta is sin theta minus pi by 2 to plus pi by 2 into ay cap. So by applying the limits, E is equal to lambda divided by 4 pi epsilon naught r sin pi by 2 upper limit minus sin of minus pi by 2 into ay cap. So E vector is equal to lambda divided by 4 pi epsilon naught r sin pi by 2 is 1 minus sin of minus pi by 2 is minus 1. So E is equal to lambda divided by 4 pi epsilon naught r into 2. So E is equal to lambda divided by 4 pi epsilon naught r into 2. So ay cap, electric field intensity is equal to lambda divided by 2 pi epsilon naught r into ay cap. So this is the total electric field at a point P due to infinite line charge. This equation represents the electric field intensity is inversely proportional to the distance r. So if the distance decreases, then the electric field increases. Again, this electric field intensity is directly proportional to the density of the line charge. Lambda represents a line charge density. So if the density of the line charge increases, again the electric field increases. So by applying Coulomb's law, here we have found the electric field intensity at a point P due to infinite line charge. Thank you.